Okay, so today what we're going to talk about is we're going to talk about combinations, and we're really going to try to think of this as like through real world examples. And what we're going to try to do is we're going to try to connect this to the basketball problem that we did yesterday. So I want to kind of intermingle these things and see how they're related. So let's read this first one and kind of work through this first one and then kind of expand it from here. So it says a hotel supervisor by teams of 6 security guards at any given time. If there's 18 security guards available, how many different ways can we order these guards? And when I'm thinking about how I would even think about setting this up, is I would just think about my options. So I'm going to have to pick 6 people. So 1, 2, 3, 4, 5, 6. And then when I pick the 6 people, I think of how many choices I have. Well, I have 18 choices here. And I have 17 choices here because I took a person. And then I have 16 choices here because I took a person. And then 15, and then 14, and then 13. And each of these 18 are completely different choices because obviously, like, they're all different people. So you do have all 18 of those choices. Now, the hard part is, I don't really care in what order that I got the security guards. It doesn't matter if I picked... I don't know, if you make up a name for a security guard, Mark. So let's say you picked Mark first. It doesn't matter if you picked him first or last. So it really doesn't matter in what order that you put any of these people in. So I have 6 people that I could order in different ways. Meaning that if I have 6 people that I could order in different ways, how many choices did I have for the first spot that didn't matter? Well, 6. 6 of the people that I had to choose 6 people, so I didn't really care what order that I got any of those 6 people in. Or for this one, after I've used one person up, 5. There's 5 different choices I could have made for my second person. And then I could have made 4 choices out of the people I picked there. Then 3, then 2, then 1. And this, if we multiply all these fractions together, would be the total number of ways that these things can be chosen. In probability, we have a faster way of writing this. The faster way of writing this idea, or this choose example where the order doesn't matter, would be 18 choose 6. And it does this automatically. Like the formula for this would be 18 permutation 6 over 6 factorial. But the thinking through that isn't really as important as understanding the idea of, oh, I have this many choices, and my overlap or my overcounting goes down like 6, 5, 4, 3, 2, and 1. And we can make sure that these things are the same way that we just said. So let's just go 18 times 17 times 16 times 15 times 14 times 13. And that's a lot of combinations, but then when you divide that by 6 times 5 times 4 times 3 times 2 times 1, it reduces our combinations. And then if we actually put this combination in our calculator by going to math, probability, this, whoops, I guess I would have to do 18 then that first. We would see that we get the same answer. So this is kind of how we do combinations. Combinations are order doesn't matter, and so we generally see these things as like 18, so how many you start with, choose this many people. And it kind of works really nicely like this. We're going to look at our basketball example and see if we could set it up using combinations. So let's try it. So if you think back to yesterday, we did this basketball example, and it's like, how many ways can I make 1 out of 3 shots? And we know from yesterday when we thought about it, it was 3. Let's see how this choose example works. This, for us, would be we have 3 shots, and we want 1 to be a winner, so 3 choose 1. The other way you could think about it is, again, because you only care about the winner, and you don't care about which shot it happens on, you have 3 choices for the winner to happen, but since you have only 1 winner, you can only order that winner 1 way. So it would be 3 over 1, which becomes 3. Let's change up the problem. Let's say now I want to make 2 out of 3 shots. So if you want to make 2 out of 3 shots, again, we said yesterday that it would be 3 choices, but let's see why it works out to be the same. This would really be 3, choose 2, because I have 3 shots and I want 2 makes, so 3, choose 2. Well, this, if you think about how it would be written, you would have 3 different shots that you could make the first one, but then after you've made one, since you only want to make one more, you only 2 different places that you could make that. Well, now we have to count the overlap. Did I make the shot first, or did I make the shot second? So that maybe I made it first, maybe I made it second, so that's over 2, and that's over 1, which that would be 6 over 2, which gives you 3. So we can kind of see how these probabilities work out pretty nicely. We're going to do a couple more, but you'll start to see this idea of 3, choose something, and then we're eventually not going to calculate this longhand anymore. We won't calculate this longhand like by doing this. We'll probably do it shorthand, like using this probability symbol. Okay, in a lotto, you draw 7 different numbers, and you choose from the numbers 1 to 48. How many possible selections are there? Well, if we're going to do this, we're going to say, okay, how many number choices did I have? 48. And how many numbers am I choosing? I'm choosing 7. So 48, choose 7. And so again, you just pull out your calculator. You could do this longhand, but we are not going to do that anymore. We're going to go the short way. That's 48. Math, probability, 7. And that would be it. Again, this works every time the order doesn't matter. So anytime the order doesn't matter and you want to know how many ways that you can do something, you just put this in. This is probably the most common probability thing. It's like this choose, because order generally doesn't matter. Let's do our last example. This is the example that I think is the hardest to wrap your mind around, but once you got it, it's pretty easy. So it says we're going to pick 4 cards out of the deck of 52, and we want to know if we only want 1 card to be king. So I do it this way. Let's do our choices for our king first. So if I look at this, I go, well, I have 4 kings in the deck, and I don't care which one I get. I just need to make sure I get 1, so I'm going to do 4, choose 1. And then, now I have to pick some other cards. So now I need 3 different cards, because we already picked 1. So now we're going to have 3 different ones. So we're going to say, whoops. If I think about how many cards are left in a deck, because you don't get all the cards. We get everything now that's not a king. So there should be, out of the 52 cards, there's 4 kings in the deck, so 52 minus 4, there's 48 non-kings in here. So if I already got 1 of my cards and I have to draw 4, we'd have 48, choose 3, because we only want 3 of these cards. And that's how many ways that you can get 1 card to be a king. We'll put that in a minute. Let's see if no cards are kings. Well, that one's pretty easy. We have 48 choices, and we want to choose 4 cards. So we just reduce the amount of cards that are in the deck. That's how many ways it would be right there. So we'll figure that out in a second. And then they go, at most 1 card is a king. So if you think at most 1 card's a king, that means there's no kings and there's 1 king, which means we already did 1 king, because this is the number of ways for 1 king right here, and this is the ways for no kings right here. So if I add the amount of 1 kings plus the amount of 0 kings, we should get at most, or this statement, k is less than or equal to 1. So we're kind of finding these. These are technically not probabilities, but it's kind of like probabilities. So we're finding these in each of this spot. So if we just add these 2 things together after we find it, it should be this. So let's find those things. So I do 4. Whoops. 1. Probably really don't have to do that because that's just 4. If you don't know why that's just 4, I would spend a little time working that out longhand. This one is a little bit trickier to do, so that's a big number. 69184. 69184. Okay. Let's do the second one. This will be easier to type in. Just gonna delete the stuff that I don't need. So we got 48, and we want to choose, we get all four cards this time. That's going to be 1945. So that's a little bit bigger, but that makes sense. 80. Because I'm not reducing the amount of choices I have for my first pick. Well, then we want both for this king thing, so let's add those together. So, plus 69184, which is a big number, 263764. But that's the basic idea behind these things. If you want to find the combinations, all you have to do, and it's the same way every single time, is use this button on your calculator, because it will figure out the choices for you. But you just have to know that the order doesn't matter, kind of how this is set up in that way. Okay. Try the different problems today. If you get stuck, let me know.